Brings us to our second talk in this session. Oh, Alok, are you here?
Yeah, I'm here.
Can you share your screen?
Yes, that's what I'm doing right now. Can you guys see my screen?
Yes, looks great. I can hear you.
Great.
Fine. Perfect. So Alok is going to talk about data transfer and reuse analysis tools for GPU offloading using OpenMP. He's at Stony Brook University, and he's a graduate student. He's doing his PhD under the guidance of Barbara Chapman in the area of high-performance computing, with a focus on program transformations for automatic GPU offloading with OpenMP. And looking forward to this talk. You have the floor.
Thank you, Hannes, for the introduction. So, hello, everyone. So today I will be talking about a tool that we developed, data transfer and reuse analysis tool for GPU offloading using OpenMP, a project which is done under the collaboration of Stony Brook University and Brookhaven National Laboratory. So the first question that might come to my mind is why GPUs? Now, owing to their extensive parallel architecture and energy efficiency, GPUs are suitable for several high-performance applications. Looking at the current trend in supercomputers, we see that 7 out of the top 10 supercomputers use some form of GPU combination. GPUs are becoming highly important in the HPC industry. But what makes GPUs so special? Let us take an example of our friend Dave here. Dave is excellent at working with bricks and can work on, say, 50 bricks in an hour. But what happens when Dave has to do the same work on, say, 1,000 bricks? It will take him 20 hours to complete the job. In comes Susan and say, hey, I have a workforce of 100 people who can, maybe individually they might be slower than Dave. Say they can work on 50 bricks in 2 hours, but together they can work on 1,000 bricks in less than half an hour. This will definitely speed up Dave's work and take a lot of burden off his shoulders. In essence, this is how a GPU works. So shall we port all our applications to GPUs and be done with it? Easy peasy, lemon squeezy? Unfortunately, no. Porting an application to a GPU comes with its own set of challenges. An application which is written in CUDA will run well on NVIDIA GPUs, but might not run on AMD GPUs. Similarly, applications written in OpenCL has lower performance on NVIDIA GPUs. On top of that, writing an application in lower level languages like CUDA, well, it's a pain in a special place for any application developer. Now, say even if we hire an expert in these languages, we still need to decide if the code is parallel enough to be offloaded to GPU or not. For instance, let's take a look. Let's say about matrix multiplication. It's a highly parallel application, but using a GPU to multiply 2, 3 plus 3 matrix is like killing a fly with a gun. And finally, the topic of today's discussion, data handling. CPUs and GPUs use different physical memory. Before doing any computation on GPU, we need to make sure that data is synced between CPU and GPU memory. Often, this results in a lot of execution time spent in data transfer between these two devices. Now, the problem of portability and programmability can be reduced to a large extent by using a directive-based language like OpenMP, which, as we all know, is the de facto programming model for node-level parallelism in HPC. And ever since 4.0, it also provides GPU offloading support. Not only does OpenMP provide support for data movement in the form of data map directives, it also gives the freedom of implicit data movement to the compiler developers, meaning the user can leave data movement to the compiler, a feature which is actually missing in CUDA. It has both its pros and cons. For instance, a compiler like Clang, it adds some implicit data transfer between CPUs and GPUs, but that does not give adequate performance. Why is that so? Let us again have a look at Dave and Susan. Before Susan's company can start their work on the bricks, Dave needs to send the bricks across to Susan. And after they are done with their job, then Susan needs to send the bricks back to Dave. This is true for any GPU offloading. Before the computation starts on GPUs, we need to transfer the data from the CPU to the GPU. And after the computation of the kernel is complete, we need to get the data back to the CPU. As mentioned before, OpenMP does provide a data map directive to explicitly make these transfers. But what happens if the programmer does not explicitly move the data between the two devices? OpenMP suggests that OpenMP suggests the compilers to transfer all data to and from the GPUs and let the compiler handle data transfer. A compiler like Clang will implicitly transfer all the data which are used on the GPU both ways, that is from the host to the device and the device to the host, which might not be the best thing to do every time. Also, there can be cases where the same data is used in multiple kernels. Currently, in implicit data transfer, Clang will always transfer all the data for each kernel. So suppose, let's take an example. Dave wants to color all the bricks in blue, then draw a smiley face on all of them, and then stack them in a particular order. For that, he raises 3 work requests with Susan. Now, what's happening in implicit data transfer in Clang is that first Dave sends out the bricks to Susan, who colors them blue and sends it back to Dave. Now, Dave again sends out the bricks to Susan, who draws smiley faces on them and sends it back to Dave. Again, Dave sends out the bricks to Susan, who finally stacks them in a required order and sends it back to Dave. Irritating, right? Of course, if the programmer explicitly adds appropriate map clauses, they can avoid these multiple transfers and transfer the bricks only once in the start and bring them back once they are stacked in the required order. Our tool is an attempt to analyze this reuse between multiple kernels and add the appropriate map clauses to transfer the data between a CPU and the GPU. Now, this tool is a part of a bigger project, Program Transformation for Automatic GPU Offloading using OpenMP, which also happens to be my PhD topic as well. In this project, we need to identify parallel regions in C or C++ code and generate multiple kernel variants, which can be offloaded to GPU using OpenMP. Then we use some static cost model to analyze which of these variants is best suited for offloading. And then that source is returned back to the user. We are implementing multiple optimizations as different modules. Data reuse analysis is one such module of this project. Now, this work is the part of the Exascale computing project, which is a major DOE project that aims to deliver 2 capable exascale systems by the year 2022. ECP works on a diverse set of applications, including code from chemistry, energy, physics, national security, etc. And most of this code uses OpenMP for parallelism, and work is already underway to use OpenMP for offloading GPU codes as well. It is a big part of the Exascale initiative. I, for once, am working on one such library, the grid library, where we are trying to automatically offload suitable kernels to the GPU using OpenMP. Now back to our data reuse analysis. In data reuse analysis, we design and develop a compiler framework which can recognize data reuse opportunities in an application and automatically insert pertinent OMP data map directive to the source code. Remember, it is a part of the project which inserts target directives to kernels to offload the code to GPUs. So the assumption here is that kernels are already identified and marked with the target code. So now just let me give you an example of what we are targeting at. This is a naive version of multiplying 3 matrices, A, B, and C, and storing the result in T. Here we have 2 kernels, which reuses a temporary matrix temp between them. At the start of the project, what we aimed at generating, and we aimed at generating and inserting target data map directives to retain these matrices on the GPU for the duration of both the kernels. Well, our tool actually gave a better result, which we'll be showing later. So this is the workflow that we follow in our implementation. We parse the AST and identify the kernels present. We parse the AST and identify the kernels present in the code. Basically, we search for OMP target regions in the code. Once a kernel is found, we do a live variable analysis on all the data used inside the kernel to identify whether the data need to be sent to the GPU, or it needs to be brought back from the GPU, or it might need to go both ways, or whether the data is private to the target region and need not be transferred at all. We also save information like location of the kernel and what are the places in the code where a particular variable is used. Next, we perform two checks on the kernel itself, loop check and proximity check. In loop check, we analyze if the kernel is called from inside a loop or not, as this is a prime contender for data reuse as in every subsequent call to the kernel. They might be reusing the same data again and again. We treat each call to the kernel from inside the loop as a new kernel. Next, we do a proximity check for two kernels. Currently, two kernels are considered to be in close proximity or to each other if they are called from the same function. We are looking at how to extend this to different functions. Subsequent call to kernel called from within a loop automatically qualifies to be in proximity to each other. Once we have identified kernels close to each other, we check for common data between those kernels. Now remember, we are doing this in compile time, so we have no idea of the actual data that we might get at runtime. Here we are only comparing the variables used in the kernel as we analyzed in our live variable analysis. Once we find that there are variables used in multiple kernels, we check if they are used on the host between the calls of these kernels or not. If no, these variables will contain data which can easily be reused between multiple kernels. We update this information in our data reuse table, which is a data structure we are using to identify data reuse. If the data is used on the host between the two kernels, we check if the data is an array or a scalar. If it is an array, then well, that is out of that candidate can be discarded and we cannot reuse that data. We just drop that entry from the data reuse table. If it is a scalar, we maintain it in the data reuse table, but keep transferring the values between the CPU and the GPU. We do this to avoid calls to memory allocations on GPU for every kernel call. Once we have identified the data which can be reused on the GPU, we modify our source code using information from this data reuse table and return this transformed source code back to the user. Now, this is a small demo of our tool in action. Let me just play the video for you. Is the video visible?
Yes.
Okay, great. So here you see our 3-matrix multiplication code with 2 kernels. And we will be running our tool on this particular code. So first it is just showing the result, the actual code. Now it shows the result of the live variable analysis, what are the data inside each kernel and how they should be used. Next, it does the loop and proximity check. Once the proximity check is done, it collects data reuse info as to what are the data which are shared between the kernels and what are the data which needs to go in the kernel, what needs to come out of it. Then it shows where the modified file is kept. When we open the file, we see that it did not touch the code without target region, and it inserts pertinent data map directive wherever it was required. So now we found something interesting here. Let me stop this and let's go back to our presentation. You see, on the left, you see what we initially envisioned as to what our tool will do. On the right is the code that was generated in our demo. After the analysis, our tool decided to only keep data on the GPU for the duration it was required. That is, kernel 1 did not need matrix C and D, while kernel 2 did not need matrix A and B. Hence, these matrices were not retained on the GPU for these kernels. Only the temp matrix was retained on the GPU for reuse for both the kernels. In this way, our tool returned a better code than what we initially aimed at. We developed and ran our tool on the local Civils cluster at Stony Brook University using one NVIDIA Tesla V100 GPU. Our tool actually works on Summit cluster as well, but I got access to Summit recently and the results are not included in this paper. For the compiler, we used our Solve compiler, which is yet another project in ECP, which develops a compiler based on LLVM. For the development of this tool, we use the version of Solve using LLVM version 8.0. Currently, Solve is updated with the latest LLVM, but we have not ported our tool to the latest version. So you won't find OpenMP 5.0 features being supported in this tool. This is something we are working on right now. For our experiments, we used 4 micro benchmark applications and 6 applications from the Rodinia benchmark suite. We modified these applications to remove any explicit data transfer mentioned in the code. We refer to these modified code without any explicit data transfer as the base code. Then we ran our tool on these base code to generate a code which we refer to as the optimized code. We built both these base code and the optimized codes using Clang and executed them 10 times each to collect the average runtime for each code. We also collected some profiling data, which we'll be discussing in the next slides. The first data that we collect was how much data was transferred between the CPU and the GPU. For each application, we saw considerable amount of data reduction from the base code when compared to our optimized code. For instance, in 3 matrix multiplication, we observed that more than 2 GB of data was transferred between the host and the device in the base case. In contrast, in our optimized code, only 763 MB of data was transferred, a reduction of 66.67% in data transfer. Now, in application like Rodinia's LU decomposition, in the base case, 5.5 terabytes of data was transferred between the host and the device, as compared to only 1.5 gigabyte of data which was transferred in the optimized code. This is a huge reduction of 99.97%. Also, in Laplace equation, it transferred 1.2 terabyte of data in the base case in comparison to only 61 megabyte of data in the optimized code, with a reduction of 99.9%. We observed a tremendous reduction in the amount of data transferred between the host and the device, with BFS being the lowest at 47.7%, still a huge difference of more than 4 GB. Now we compiled a code using Clang compiler for NVIDIA GPUs. So Clang uses CUDA in the backend for GPU offloading. So we also collected information on how many times different CUDA APIs were called. We saw that the majority of the time was spent in 4 CUDA APIs: CU memalloc, CU memfree, CU memcopy H2D, and CU memcopy D2H. The names are enough to tell us what they do. We found that apart from data transfer, the number of times memory allocation and free is called is also reduced a lot after using our tool. For instance, in Laplace equation, each of the 4 APIs are called around 25,000 times in the base code. Upon further analysis of the base code, we discovered that it was calling a kernel from inside a loop which iterated for 5,000 times. In our optimized code, the data transfer for the arrays were moved outside the loop. It dramatically reduced the number of times the data was moved between the host and the device in our code. So in the optimized code, each of the 4 concerned APIs were only called around 5,000 times only, with the reduction of total number of API calls by 79.99%. We observed this reduction in the number of times the total APIs are called in all cases, with a maximum reduction of 99.96% in LU decomposition and a minimum of 37.04% reduction in matrix multiplication. These are considerable reduction in the number of times the APIs are called. So does this reduction mean anything? Do they have any impact on the runtime of the application? Well, we collected information on the runtime of each application, and the results did not disappoint us. As you can see in the plot, the purple colored bar represents the compute time of the kernel. This time does not change for both cases, both the base and the optimized case. This is expected as we did not change anything in the kernel code, but data transfer time reduces in all of the cases. The numbers at the tip of each graph represent the time taken for data transfer only in seconds. Okay, we did not get much gain in applications like matrix multiplication or Gaussian elimination or SAXP or BFS or even particle filter. But we also did not lose anything performance-wise. Now look at other applications. The performance gain that we see in applications like Laplace or LU decomposition is tremendous. In Laplace, where we used to take almost 36 seconds to transfer data in the base code, it took only 0.35 seconds in the optimized code. Similarly, for LU decomposition, transfer time reduced from 282 seconds to less than 0.1 second. In k-nearest neighbor, the difference between data transfer time and compute time is so huge that compute time is not even visible in this graph. And in not a single application did we see any loss of performance due to code introduced by our tool. We ran similar experiments using GCC. That is, we built the base code and optimized code using GCC 9.1 compiler and got somewhat similar results. Well, as expected, GCC performance was much worse than Clang. But this work is not to compare Clang versus GCC. In GCC as well, we found that there was no loss of performance in any case. And in some cases, there was significant improvement in the performance. What does it mean? It means that our tool, though built using LLVM Clang, produces an output which is portable across other compilers as well. Optimizing GPU memory management, where data movement has to be managed explicitly, has been explored in a variety of research. Yet these research do not provide insight into utilizing data reusability on GPUs, especially for implicitly managed data between multiple kernels. To conclude, using our tool, we were able to gain significant performance improvement in some of the applications. No loss of performance was observed in any of the applications. My favorite part for our tool is that we return the modified code back to the user, which means the user can accept or reject the transformation introduced by our tool. This can help in cases where the user does not want to retain data on the GPU, or they just want to transfer all the data all the time. It's left upon the user whether they want to keep the modification that we have done or not. As a future work, we are working on extending the proximity analysis to multiple functions. We are also looking at how to better utilize unified memory to reduce data transfer. And we will be working on adding OpenMP 5 features into our tools. Apart from my project on program transformation for automatic GPU offloading, this tool can help other auto code generation tools like DOMCC or AutoPara as well, which you can generate OpenMP code for GPU offloading. So fingers crossed for that. Well, that's it from my side. You can find our work on the given GitHub location. And if you have any questions or suggestions, please.
Thank you very much. Great talk. We already have 2 questions in the chat.
Let me just
read out your question yourself.
Yeah, let me just go through the chat. I am not able to see my chat. Why am I not able to see my chat?
Let me read the question for you. Does the data reuse analysis consider the value of the variable? For example, an array may be used on the host between 2 target regions. However, the host only reads the array so that the corresponding copy on the target is still valid. Do you consider this case?
I am still trying to open my chat window. Actually, where did it go? Ah, there is it. Okay. Consider the value of the variable. No, it does not consider the value of the variable because the value, as I said, that this analysis is done at compile time, not at runtime. So most of the time, we will not even know what is the value of the variable, especially when we are talking about huge arrays. So we are not really, right now, we are not really concerned about the value which is contained inside the variable, but we are just comparing the variables. We are doing live variable analysis and comparing the variable to see if the same variable is used between 2 kernels. And we are also trying to see if the variable in any way is modified or reused on the host to eliminate conditions where there is a possibility of updation of data on the variable between the kernel calls.
Right. I think the last part was answering the question. So like you determine already if it is modified on the host, right?
Yeah. And the second question is, can we use this tool for Fortran code? I wish we could, but unfortunately, no. Right now, we have not done this for Fortran. It's only for C and C++. Right. And when can we use it? I wish yesterday, but sorry.
I mean, the question is probably not to you, but to some of the other people here in the room. When do we have a Fortran front end for LVM?
Well, I can say one thing. If someone can take up the project for implementing it in Fortran, I will provide my assistance to help in any way possible.
So to answer the Fortran question, it will take a little while until we get a proper offloading Fortran front end. So we're talking like months away. There was a comment.
The talk Monday afternoon would help on that. Tuesday afternoon, the Fortran front end talk.
Mm-hmm.
Right.
To follow up on the previous question, so you.
Mm-hmm.
It sounded like if it's only a use and not a death, that you don't have to retransfer to the device. But do you insert target updates so that you're sure that you get the right value on the host? And if so, have you considered trying to generate target updates back to the device after the definition on the host?
That is actually a good suggestion. I can actually keep it for my future work as well. Thanks a lot for that. Because if right now what we are doing is we are considering the addition of data at the start and end of a kernel. And what you are saying is that between the kernel, if there is any data movement, right?
Right.
Yeah, so that is something we can consider in our future work. Yeah, thanks for that.
Yeah, it'd be interesting to see if you could come up with an analysis that could determine when the right choice is to use target update as opposed to mapping back and forth. It's not 100% clear. Certainly, if it's a small piece of data that's being updated, that would be preferable to moving all the data off and back.
Okay, we're already at the top of the hour. I'll keep my questions to ask them offline later. And
Sure.
thank you for your talk.